Okay, so this is our last example of using the graphing strategy. We do have one more example after this, but it's kind of a different type of problem, so we'll get to that when we get to that. We're going to go through the same 5-step process to graph this function. Starting with step 1, find the domain. The domain of this guy is going to be the same as the domain of the natural log function, because this is a product of a polynomial with a natural log, and the natural log is the only function of those two that has a domain restriction. It's the set of all positive real numbers. So my domain of this function is also the set of all positive real numbers. Looks like that as an interval. Okay. Now let's find some intercepts. Let's start with the x-intercept this time. If I set y equal to 0, 0 equals x to the 5th times the natural log of x, then either x to the 5th or the natural log of x is equal to 0. And in each case, I get a different x value that causes that to happen. For x to the 5th to equal 0, x would have to equal 0. For the natural log of x to equal 0, x would have to equal 1. So now we ended up with two x-intercepts. 0, 0, so the origin again, and 0, 1. To get y-intercepts, I plug 0 in for x. However, this is undefined at 0, so there is no y-intercept. No y-intercept. Okay. Vertical and horizontal asymptotes. What can we say about those? Well, the x to the 5th does not have either of those. This is not a rational function where we're looking at a denominator and trying to find vertical asymptotes. However, it does have a vertical asymptote because the natural log function has one. If you remember, the natural log function looks like this, right? Where it has a vertical asymptote as x approaches 0. Do we still have that asymptote after we multiply this function by x to the 5th? Well, again, in order to show, what you're doing there is you're taking the limit as x approaches 0 from the positive direction to see where this graph is going. If it goes to negative infinity, vertical asymptote. If for some reason it goes to positive infinity, then we have another vertical asymptote, but it's just the graph will go this way. If it's some finite number, then we don't have either. However, to evaluate that limit, once again, you need L'Hopital's rule, which we don't talk about in this class. We talk about it in a full calculus class. So we're stuck using the numerical approach for evaluating limits. The goal here is to plug in numbers that are very, 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 very close to 0, but still positive. So I don't even need to get that close to 0 to see what's going on here. Let's plug in, for example, 0.001. If I plug 0.001 into this function, first thing I'm going to do is take it to the 5th power and then multiply that times the natural log of 0.001. Use a calculator, of course. This is not something you want to try and do by hand by any means, but we get this, equals negative 4.6 times, I think I put the wrong thing in mine. Hold on. Put 10 in there. 0.001. Yeah, sorry. I had to plug something into my calculator because I think I had done something wrong. So when you plug 0.001 in there, you're going to get not what I was about to write. I had written the wrong thing down. Approximately negative 6.9 times 10 to the negative 15th power. Okay, so what that tells me is that I'm getting something very, very close to 0, right? And if I'm getting something very, very close to 0, it's not shooting off to negative infinity. It's not shooting off to positive infinity. So there is no asymptote of any kind here. So no horizontal asymptote or vertical asymptote. However, I want to make note of what I found here. The limit as x approaches 0 from the positive direction of my function x to the 5th times the natural log of x is a very, very small number, and numerically, I'm going to assume that this is going to go to 0. okay? The reason that matters is because this function is not defined at 0, but it is defined for everything greater than 0. So when I sketch my graph, I kind of want to see what this is approaching so that my graph is accurate. Let's leave that there for now. I think we've dealt with the intercepts and the asymptotes and all that stuff. Let's talk about step 2. We need a derivative, y prime. I need the product rule again, so I'll take the derivative of x to the 5th first, 5x to the 4th times the natural log of x, plus x to the 5th times the derivative of the natural log of x, which is 1 over x. This becomes x to the 4th, and now I have a common factor of x to the 4th that can be factored out. So I get x to the 4th times 5 natural log of x, and then I only have a 1 left behind here when I do that. Remember, we're looking for where this thing gives me critical values. Even though it's not defined for all values of x, it is defined everywhere that this domain is, that the original function is defined. So I'm not going to get any I'm not going to get any critical values where the function is not differentiable. That means I can only get critical values when this is equal to 0. So clearly, if x is equal to 0, or if x to the 4th is equal to 0, then x will equal 0. But what about if 5 times the natural log of x plus 1 equals 0? Well, if I subtract 1 and divide by 5, I get the natural log of x equals negative 5 halves. Negative 1/5. I don't know why I get that. Negative 1/5. Solve for x by taking e to the power of both sides. X equals e to the negative 1/5 power. So that is another solution to this. X equals e to the negative 1/5 power. But remember, we're going to be kind of approximating these things with decimals to make the graphs easier to work out. This is approximately 0.819. So 0.819. Okay, those are my critical values. So I create a sign chart now. I put those critical values down. And the 0 here, I'm going to put as far to the left as I can put it, because I don't want to think of anything to the left of that as being an interval that I need to check. Remember, this function's not even defined to the left of 0, so nothing's going on over there. I do want to plot 0.819, which is e to the negative 1/5, and see what's going on there. So picking a test point over here, if you plug in, it's going to be easier if you want to do this in your head, to plug in e to some power that's less than negative 1/5, because that's definitely going to be in here. So for example, e to the negative 1 power. If I plug that in for x, the natural log of that is just negative 1. Times 5 is negative 5, plus 1 is negative 4. That's negative. X to the 4th is positive no matter what I plug into it, except for 0, of course, because I'm raising it to an even power. So that's positive times negative, which gives me negative. So y prime is negative there. If I plug in a number greater than this, say 1, then I'm going to have, for example, 5 times the natural log of 1, which is 0, plus 1, which is 1, times another positive number that's positive. So I get y prime is positive. That means our function is decreasing here, but it's increasing there. Okay? So not only do I have a point that's acting as a critical value, but I'm going from decreasing to increasing. So my first derivative test tells me I have a local minimum there. Local minimum. And it occurs where my x is equal to 0.819. What about the y coordinate of that point? Well, I would have to take my number here and plug it back into the original function, which you can use a calculator for. And what we end up with is negative 0.074 as the y coordinate for that. Okay? That's the only local extremum that I get. So I'm going to move on and go ahead and do step 3 next, concavity. We need a second derivative. Let's take the second derivative using this version of my first derivative so I can apply the product rule to it. Derivative of the first function would be 4x cubed times the original second function, 5 natural log of x plus 1, plus the first function, x to the 4th, times the derivative of the second function. Well, the 1 goes to 0. Natural log of x has a derivative of 1 over x times 5. That would look like 5 over x. okay? This x will cancel with one of those and give me x cubed. So really what I have here is 5x cubed. And then I see a common factor of x cubed that can be pulled out. So I'm going to factor x cubed out. That leaves me with 4 times the natural log of x, 5 times the natural log of x plus 1, plus this, I factored the x cubed out, all I have left in there is a 5, okay? Let's multiply that 4 in. So I'm going to have x cubed times 20 natural log of x. 4 times 1 is 4. Then adding that 5 to that, I get 9. We want to set that equal to 0 and solve. I'll get two solutions from this. X equals 0 or x equals e to the negative 9/20. Now solving this guy, setting 20 ln of x plus 9 equal to 0, when I solve that, it's going to look really, really similar to how I solved this. I would follow very similar steps. I just have different constants in there. Hopefully you can work out how I got this. It's very straightforward, okay? E to the negative 9/20. Let's plug that into a calculator so we can get a decimal that's going to help us when we actually graph things. This is approximately 0.638. That's going to be the approximation that I use, okay? So now, create a sign chart. And remember, even though 0 came out as one of our solutions to this, it's actually not a usable value, because even though if I plug a 0 in here, this comes out to 0, I can't plug a 0 in there. In fact, I should have made a note of that up here as well. So when I think right here where I said x was equal to 0, it can't equal 0 because this function's not defined for that. So really I just got one critical value. Okay, I'm still going to put the 0 on my sign chart because it's the left boundary for my domain, but I do want to include this 0.638 there. And now we're plugging test points into our second derivative. So for my second derivative, I can not use the decimal for the sake of checking. What I could do is I could plug e to the negative, say, -1, that would be smaller than this, into this right here. E to any power is positive, so x cubed, when I plug e to the -1 into this, will come out positive. When I plug e to the -1 in here, natural log of that gives me just -1 times 20, that's -20, plus 9 is -11. So I have a positive times a negative, which is negative. Okay? Next up, I'm going to pick something larger than this, let's say 10, maybe, or in fact, because of the natural log in there, let's plug in 1. That's an easy number to work with. 1 is larger than this. Natural log of 1 is 0, plus 9, that's positive. And then 1 cubed is also positive. So positive times positive gives me positive. That means we are concave down here, but we're concave up there. Okay? Now with all that in mind, I also have a point of inflection right here because I have a change in concavity at that point. So what is my point of inflection? Well, 0.638 approximately, that's the x-coordinate. To get the y-coordinate, I would plug that back in, but to the original function, okay? And if I did that, what I would end up getting is, did I write that one down? I thought I wrote that one down somewhere. Maybe I didn't. No, I appear to have left that off. Let me compute that really quick. Off to the side here. What did I say? I wanted to plug in e to the negative 9/20 is what that was. All right, so that comes out to approximately negative 0.047. That's that point of inflection. Okay? So we've got a lot of useful information here. Let's start putting together our shape chart. So for number 4, create a number line, find all relevant values that were on either of these sign charts. 0 is on both, and that's kind of like a boundary. We don't go any further left than that. 0.638 was there. I'll put a 0.819 there, and that gives me 3 subintervals where I want to look at the shape of my graph, okay? So the first of these two values, 0.638, we're concave down to the left of that, But if we're looking at numbers less than that, those numbers would also be less than 0.819, and we're decreasing in that interval. So concave down, decreasing, that would look like this, generally, right? Here, we're between 6.38, so we're larger than 0.638. We're concave up here, but we're still less than 0.819, so we're still decreasing there. Concave up and decreasing, what would that look like? Well, if we're concave up and decreasing, that's going to look like kind of like this. So again, decreasing but concave up. Finally, if we're looking at values larger than 0.819, then they're also going to be larger than 0.638. So we are concave up and increasing there. Concave up, increasing. That's going to look like that. Okay? So that's our shape chart. Let's go ahead and graph our function as best we can. Okay? Look for any relevant numbers in the points that we want to graph. So I want to graph the origin because that's my x and y intercept both. So I'll put a point there at the origin. 0, 1. So I want to make sure I include 1 in there and put a point there because I have an x intercept there. What else? Well, we have 0.638 and 0.819. Those are both between 0 and 1. So I just need to make sure that those values appear in that interval somewhere. And then my y coordinates, looking at any points that occur here. Oh, I just realized I wrote this incorrectly. If it's an x-intercept, that should have been 1, 0, not 0, 1. Swapped my coordinates. Other points of interest are my local minimum. My local minimum has a negative y coordinate. So let's put a negative 1 in there. That's enough to capture that. And then I have another negative y coordinate right here. So I need to include that. So it looks like most of the information for my graph that I found is going to be in this small little window. Maybe I should have made that a little bit bigger. But that's okay. Now let's see if we can get to the graph itself. So one of the things that we said all the way up here was that the limit as x approaches 0, but from the positive direction, is 0. So I'm thinking of that as x being 0 and y being 0. I'm thinking of that as the origin. But remember, I have to actually get rid of this. We don't actually have an x-intercept at the origin because our function is not defined at 0, so I should have left that off. When I put this point here, because our function's not defined there, I really should have made that an open circle. So let me correct my mistake. I'm going to make that an open circle. Now, we have some important areas that we need to, some points that we need to plot. So first, 0.638 negative 0.047. That's a point of inflection. So 0.638 is a little bit more than 1/2. And then it's got a y value that's pretty small. It's going to be like that. And then I have a local minimum a little further to the right and a tad further down below that. So it's going to be like right here. Okay, so this is a point of inflection. That's a local minimum. Looking at what my graph does, we are concave down from 0 to 0.638. That's here. So I made it kind of concave down, if you can see that. We're concave up and decreasing on this next little interval, so it's going to do something kind of like that. Okay, then we are concave up and increasing everywhere past that, but I also have this x-intercept right there. So my graph is going to do something like that. Okay, so there's kind of a subtle little change in concavity that occurs down below the x-axis, and then it just sort of explodes like that. That's what that graph is going to look like. Okay. Again, with any of the 3 examples that we did up until this point, you can go to a graphing utility like Desmos or a graphing calculator, check your answer by plotting, like inputting that function and looking at the graph. You should get something similar to what we drew. I have one more example that I want to do. I think we can do it on this video. We're approaching things from a different direction. Examples like this one have several different answers. It just depends on how you want to use this information. But we have a function, y equals f of x, and we don't know what the function looks like specifically, but we have a lot of information about it. So first of all, this function is going to be continuous on the set of all real numbers. The next point that I have is what we call end behavior. So I know that the limit as x goes to negative infinity of my function is negative infinity. The limit as x goes to positive infinity is positive infinity. That tells me like the direction that this graph is going in the long term. We know that f of 0 equals 10. That means that the point 0, 10 is on the graph. We also have a vertical tangent line at x equals 0. That's where my slope is undefined. So I have to try to make my graph look slightly vertical just at that point right there. We know that f prime of x is greater than 0 on these intervals. F double prime is greater than 0 on this interval, negative infinity to 0, and it switches to being negative on the other interval there. Okay? So what I want to do is take these bottom 3 points and make a sign chart or a shape chart out of that. So notice the only intervals I'm seeing here are negative infinity to 0 and then 0 to infinity. So that means 0 is kind of the relevant number in there. Okay? So if f prime is positive on both of those intervals, then we are increasing on both of those intervals. If f double prime is positive on this interval, then we're concave up there. And if it switches to being negative, it switches to being concave down there. Now remember, our function is defined everywhere because it's continuous everywhere. So 0 is not like a vertical asymptote or something like that. In fact, there would be a point there and our concavity changes. So that means we have a point of inflection at 0. Okay, somewhere over here, there's a point of inflection. But we are also increasing the entire time. So let's think about what the shape of these curves would look like. Increasing, concave up, looks like that. Increasing, concave down, looks like that. Okay? So I think I have enough information to start sketching a graph. Okay? One of the things I do know is that I have a point at 0, 10. So I'm going to include 10 on my y-axis right there. I'm not going to worry about a bunch of other labels because I don't have all these decimals like I did in my last 2 examples. But I have that 10 there. And then there's a point at 0, 10. Okay? Not only that, we know a few other things about what happens at this point. We have a vertical tangent line. So my graph, no matter what it's looking like, has to kind of look vertical just at that point before switching concavity and stuff. In addition to that, we know we're continuous everywhere, so there should be no breaks or holes in my graph. We know that the graph is going to go to negative infinity as x goes to negative infinity. So my graph should go forever downwards as I move to the left and forever upwards as I move to the right because the limit as x goes to infinity is positive infinity. Okay? And then these last 3 pieces of information are for that sign chart. So I think of a graph that would satisfy all of this is something like this. So notice concave up and increasing here. Try to make it almost vertical right when we get there. Almost vertical. And then it's going to continue increasing, but in a concave down manner away from there. Something like this. Okay? Notice that neither of these ends of the graph are approaching a horizontal asymptote. It's continuing to go up, and this one's continuing to go down, which takes care of this limiting behavior. I have the point that's supposed to be on the graph. I have, as best as I could draw it, something that looks like it would give me a vertical tangent line right there. And then all of this criteria is met because I made a shape chart for it. So this is one possible answer to this question. Now, obviously, you can come up with other solutions based on how you kind of scale this thing in different directions, but it generally has to have that shape to it. Okay? So that's it for section 3.3.